Realistically speaking, any researcher or surveyor or pollster needs to have a sense of what sample size they're shooting for before they go off and start calling people or grabbing people for a study. So they need to know how many. And of course, they don't have to just be people. You could be doing research on, animals. So how many hippopotamuses do we need? That kind of thing. So there's two main brands of sample size formulas. On this page, we're going to learn about the sample size for estimating a population proportion. So that will be for proportions, for percentages, for surveys, right? For polls. These are the formulas that pollsters and surveyors use in order to figure out how many people they need to call. Now, if you look at the formula, or this formula, either one, both of them, there's a relationship here, you'll notice what doesn't enter into it at all. In no place does it ask what the population size is, because it doesn't matter, right? What matters is how confident do you want to be? That's where the Z is coming from. And then how much margin of error do you want, right? How accurate do you want to be? So those are the two things that you want to know. And that's about all that matters. And same thing over here. Now, when you have a prior estimate, what does that mean? Right? That means that you have some past study or past survey that had a p hat from it. So you have some old data, right? So prior means from the past, so old, right? And if you don't have a prior estimate, if you've never done a study on this topic before, then you would use this formula right here. And as per usual, they are in your exam notes packet. So you do not have to memorize them. You do not have to write them on your own notes packet for the exam. They're right here on this page. So right there, that whole box. All right, so both formulas must be rounded up. That's key because you cannot have a decimal of a person. You either talk to one person or two people or three people, but you can't have 1.23 people. And the error in that denominator must be a decimal. Now, why is that an issue? It's not. What happens is that error is often written as a percentage. And so you'll have to convert it to a decimal in order to make the formula work. The formula doesn't take the percent. The formula takes a decimal. That's all I'm warning you about here. And that's not a problem for the other formulas we'll learn. It's a problem for the percentage ones in particular. And just a reminder that Q hat right there is the complement of P hat, right? P hat and Q hat, probability of success, probability of failure, related to the binomial probability experiment that we learned about in chapter 6. All right, so let's practice, shall we? Suppose a researcher wants to know what proportion of U.S. college students do not have health insurance. How many college students would the researcher need to poll if, right? And poll is when they call them up, or technically you can do it face-to-face. You can do other ways, but calling is the most frequent one. And then for all parts, I want you to show your formula, your substitution, your result. So be warned. I've said that before for confidence interval questions, but I also say it for sample size questions, right? So that little phrase right there does not mean it's a confidence interval. And the fact that I write right here that I want a 95% confidence does not mean this is a confidence interval question. You want to look for the question word, which is right here. I even bolded it and everything. How many? When you want to know how many, that's a sample size question. Okay? And I even wrote it on this page right here. How many, right in your exam notes packet. Okay, so the researcher wants to have 95% confidence with a 3% margin of error. And these are the values most typically used by news organizations right around here. They'll fuss with the margin of error a little bit sometimes, but they almost always use 95% level of confidence. All right, well, I have no prior estimate. Like there's no past study here. So that means that my formula will be the one on the right because I have no prior guess. So n equals 0.25 times z alpha over 2 over the error squared. All right, now my substitution, where all the work is. All right, so the 0.25 is no problem. That's 0.25. Now the error. The error was 3%. See that? but you don't write 3 here. 3% means the error is 0.03. You convert it to a decimal and put that down here. Right? For proportion ones, it's almost always given as a percent. So I make that 0.03, and then I need to find that z up there. Well, I need alpha over 2 if I'm going to find that. Well, I don't. Let me put it this way. If I'm going to use StatCrunch, I can actually go do it right now. So StatCrunch, I would go to Stat, Calculators, Normal, because it's the z curve. We've done this before. This is from Chapter 7, and also we did it already in Chapter 9. And then I would say the mean is 0, the standard deviation is 1. That's what makes it a normal curve. I'll make the middle area 0.95, enter, and I get 1.96. There you have it. Now, if you're going to use the table or the calculator, alpha would be 0.05 because alpha and the C level are complements of each other, right? So this C level is going to give us this Z, but it's not directly. We have to kind of do the alpha over 2 thing. So alpha over 2 is 0.025. And then I can either use the bottom row of the t-table or StatCrunch, which I already did, bottom row of t-table, if you want. You don't have to if you don't want to. If you want to use StatCrunch, maybe just make a little note to yourself of how you did it in StatCrunch. All right, so 0.025 is right here. The z's are at the very bottom row, so it would be 1.960 right there. And I actually just wrote that. So if you're going to use the calculator or the bottom row of the t-table, write this information for yourself. If you're going to use StatCrunch, write this information for yourself so you can kind of remember what you did. But you don't have to show that work for me. That's more for your own notes so you know what the heck you did when you have to come back and look at this thing. Oh, and the calculator real quickly. The calculator, you'd have to use inverse norm. So second distribution, inverse norm, 0.025, 0 and 1 and left would be how the old calculators work. And if you want to use center, then that's fine also. You'd take 0.95 and use center if you have the ability. That's what StatCrunch is essentially doing. All right, so then what if the researcher wants 95% confidence still, but wants to let the margin of error be 4%? Oh, I never actually found that number, did I? All right, let me come back. Let me go back real quick. I'm just going to grab this calculator and I'm going to type that in. 0.25 parentheses 1.96 divided by 0.03, close your parentheses and square it, which is right over here. Enter. Don't forget the squaring. A lot of students do, and then they lose it, right? So make sure you square it. And it should be 1067.1, repeating, but you can't talk to 0.1 of a person. That's impossible. So that's when you must round up to 1068. Round up no matter what, even though it's only 0.1. If you go any lower, if you go to 1067, you'll lose either the accuracy or the confidence that you wanted. So you must round up. You'd rather err on the side of too many people than too few. Oh, and that's the result right here. So we have our formula, our substitution, and our result. All right, let's do it again. Formula is still the same formula. So n is 0.25 z alpha over 2 over the error squared. The substitution would be 0.25. All right, now, what did not change was my confidence. And since my confidence did not change, the 1.96 doesn't change. Right, 1.960 if you like. Confidence gives you that z, right? The confidence and the z are interrelated, right? What did change is that denominator. It's going to become 0.04. So I'm raising the margin of error. I'm letting there be more squishiness, more error in this problem. Let's see what happens. So if I take 0.25 times 1.96 divided by 0.04, close parentheses, don't forget to square it, and press enter. Look at that. Far less people, right? Because I'm allowing a lot more inaccuracy. I'm letting it be a lot more squishy. So 600.25, you cannot talk to 0.25 of a person. So that means 601 is your answer. Now you'll notice this top answer, by the way, the 1068, right about there is what most polling companies and news organizations do. That's why they're always polling around 1,000 people, because they want 95% confidence and about 3% margin of error. And that's why a lot of surveys are about 1,000 people. They're doing this, just in case you're wondering. Now, suppose that we have a 2016 study. Oh, so that's in the past, right? That found that 8.6% of U.S. college students do not have health insurance. Now, how many people would the researchers need to survey to have 95% confidence with a 3% margin of error? So we're going back to the 3%. Still want 95% confidence. So that means that the z alpha over 2 is still going to be 1.96, right? Because the confidence never changed this whole problem. So once we figured it out up here, we figured it out through the whole thing. I'm going back to the 3% margin of error for no particular reason. I just am. So I'm going back to the error is 0.03. Actually, I'm not even going to write that because I want to leave myself some space here. What I do notice is that this past bit right here is giving me a prior p hat. Is telling me p hat is 8.6%. That's 0.086 because you move that decimal 2 spots over to the left to convert it into a decimal. That decimal point, I should say. All right, so formula. Well, it's not the same formula because we have a prior study. We're not going to use this one over here, right? This one had no prior up here, right? Both A and B had no prior p hat. Right? No information from before. But part C does. So I'm going to use the one on the left. I have an old study. And so N is going to be P hat times Q hat times Z alpha over 2 over the error squared. Okay, so substitution. The p hat I know is 0.086, right? That's our p hat. My q hat is the complement of that, which is 0.914, because they have to add up to 100%. And if you don't believe me, of course, you can just type in 1 minus 0.086. There it is, 0.914. So it's the complement. They make 1. And then the parts that haven't changed. I know that this top number is 1.960 because it hasn't changed because my confidence hasn't changed. And my error is back to 0.03. And then I type all of this either in Desmos or in a calculator, right? Whatever works for you. So 0.086. If you want, you can use parentheses, but you don't have to. You can just type 0.086 times 0.914 times 1.960 divided by 0.03, close those parentheses, and square it. So it looks like that. Or if you like, you can do 0.086, close parentheses, another parentheses, 0.914, and then raise it to the 2 power. It'll get you the same answer either way. So we get 335.5. And of course, I'm showing the calculator because the calculator is actually more difficult than Desmos. Desmos is easier to work with, so I didn't even bother with that. All right, so 335.5. Which would round to 336. That's our result. Oh, I guess I should have mentioned these are all people, 336 people. Right? We're not doing hippos or anything like that. All right, now there's a lesson to be learned. I chose these examples for a reason. So let's compare the first two, right? When we increased the error, right? When I let the error go from 3% to 4%, look at what happened to the number of people that were required. It went down. Why? Well, when you make the denominator larger, see what's happening? When the denominator gets larger, the overall result gets smaller. So that leads us to a comment down here. When you increase the error, means the sample size decreases. Right? Increasing error means sample size decreases. In other words, think about it this way. You have error here and sample size here. If error goes up, sample size goes down. They're on a teeter-totter together. It's called an inverse relationship. By the same token, by the way, if you make error go down, then sample size will go up. If you want more accuracy, if you want only 2% margin of error, right, really nice tight confidence interval, then you're going to have to get a larger sample. Now, what about having a prior estimate? Well, that would be comparing, so if you want to think about it, this one was comparing A and B, right? So if you look at the two examples, this one is comparing A versus C, right? Example A versus C. What happened? Well, when we had no prior estimate at all, we needed 1,068 people. And then when we had a prior estimate, we needed only 336 people. So having a prior estimate means sample size, sorry, that's two words. I was going to make it one. Size is smaller, which is one of the reasons that polling agencies actually can get away with less than 1,068 people, because often that's because they've done previous studies. They have a clue from the past of where it is, so they don't need as many people, where the P is, that is. So they don't need as many people to figure it out for this current moment in time, because they already have a guess from back in the day.